Hi everyone, welcome back. So hopefully you've now got that exercise solution up and running. So one of the last things I want to talk about is batch runs. Now, you remember when we talked about SymPy, we said there's rarely, if you're sort of building a model in earnest, it's rarely useful to just run a model once because you could get a run of good luck or bad luck, however you wish to view it, that would then skew the results. You need to generally run models lots and lots of times and then sort of take average results over those runs. And we can do the same thing in MESA with our agent-based models. Um, and the way we do that, rather than setting up a server to run as we have before to watch the thing live, we can use a library called BatchRunner. Um, and all we need to do, BatchRunner is really easy to use because what it allows us to do is to say, I want those parameter values to stay the same. I want these parameter values to change within these ranges, and then tell it to go off and try all of those different combinations, and it'll nicely bring us back all the data. That's really useful when we're testing out lots of different combinations. So let's have a look at this in action. So if you haven't already, save take a copy of the file that you've already written, and start. So take a copy in wherever you've got that saved, and then we can start on a fresh new copy of this. So we're not changing anything from the existing one. So up to now, we've used in the disease run py file, we've just used the run file to launch a server. But now we're not going to launch a server. We're going to use the run file to specify that we want to run this model in batch. So in case we want it again, let's just comment out the 3 lines of code that are already there in the run file. So I'm just going to put little hashtags in front of them just to comment those things out. Then we can now start writing our run file for running it in batch. So as always, first thing we're going to do is import the things we need. So here are the things we're going to need. We're going to need to import from our disease model, which is the disease model file, import everything. The asterisk there means import everything. So import all of the bits in our disease model file. From NumPy, we're going to import the A-range library. We're going to use that because we're going to need to work with some floating point ranges. So you'll see why that's needed in a minute. We're also going to import from matplotlib. We're going to import from pyplot of matplotlib. We're going to import we're going to import pyplot from matplotlib, and we're going to import that as PLT, so under the alias PLT, so we can just refer to PLT from this point forward. And then from MESA, we're going to import from the BatchRunner library, we're going to import the BatchRunner class, and this is the thing that's going to do all the running in batch of our model. So type those 4 lines of code out, pause the video while you do that, and then we'll carry on. Okay, so now we've done our imports. Next, what we want to do is specify the fixed parameter values. These are the things that for every run, every combination of parameter values that we've got, because remember, if we're doing it in batch, we're not going to have a user sitting there watching it and changing the sliders. We're going to need to specify what the parameter values are. So we need to differentiate between those that we want to stay the same across all of the runs, and those that we want to adjust and try different values for. So the first ones are the fixed parameter values. These are the ones that we always want to stay the same for all the runs. So we do this by setting up a list, I've called it fixed params, and we set it up as a dictionary with label and value pairs, with the label representing the name of the variable and the value representing the value that we want to assign to that variable that we want to remain the same throughout all the runs. So width and height of the grid, we want that to stay the same, 10 by 10. I'm going to keep the initial infection at 80% here. I'm going to keep transmissibility at 50%, the mean length of the disease at 10 days, the mean immunisation duration at 20 days, and the probability of being immunised at 5%. So put this line of code now in your disease run file. So now we've set up the parameter values we want to stay the same. We now need to specify the ones that we want to change, our variable parameter values. So these are the different combinations that we want to test. So here, I'm just going to have two of the parameter values that will change. I want to try different numbers of agents in the models, and I want to range that from having 2 agents in the models up to 100 in increments of 1. So I want 2 agents to be tested, 3 agents, 4 agents, 5 agents, etc. And I want the level of movement to vary from 0, so where nobody moves, up to 1, where everybody moves on every time step. And I want to do that in increments of 0.1, so in 10% probability increments. So the way we do that down here, we can see the code. I've set up a dictionary called variable params. And again, same thing where we've got label value pairs. So the label being the name of the parameter that we want to change in this case. So value of n here, which remember is the number of agents in the model. That I want to be a range between 2 and 100 in increments of 1. And level of movement, again, I also want that to be a range from 0 to 1 in increments of 0.1. And you see here I've had to use a range, which is why we've had to import that from NumPy, so that I can do that as a floating point range, because we've got decimal places in this one. So add that line of code now. So we also need to specify the number of iterations to run for each combination. So if I've got a combination where I've got 5 agents in the model and a level of movement at 20%, how many times do I want to repeat that combination? So I've decided here to do 5 iterations for each combination. And I also need to say how long to run each model for. So I've decided on 365 time steps. Our time steps represent days in our model, so it represents a year. So basically run each combination of parameter values 5 times, and in each run of the simulation, run it for a simulated 1 year. So once we've done all that, we've set that up, we can just set up a batch runner with all that information included. So here I've set up a batch runner that I've called BatchRun, and I've set up a batch runner, and the inputs are going to be the model I want to batch run, which is a disease model, which we've imported, remember, at the start of this file. The fixed parameters are the dictionary of fixed parameters that I set up, which I call fixed params. The variable parameters equal to the variable parameters that I set up with that dictionary, which I called variable params. Iterations, that's the number of times to run each combination. So I've got that stored as the num iterations. Max steps, that represents how long to run the model for, so that's equal to num steps. That's what I called it up above. And then the model reporters we need to specify, because these are the things that we're going to get results. These are the results that are going to be output. So as before, we've got our 2 model reporters that I've put in there. So pause the video and input your this code. So you've got the number of iterations, number of steps, and then putting it all together in the batch runner. Okay, so now you've done that. Now we've set up the batch runner, we just need to tell it, which remember we've called batch run. We need to tell the batch runner to run all of the combinations. There are different functions. You can just get it to run certain combinations. We want it to run through all of them. So this command batchrun.run all will tell it to run all the combinations in that batch runner. And then once it's done that, let's store the run results in a pandas data frame, because that'll make it nice and nice to explore. So we can say run data, which is what we're going to call our pandas data frame, equals batchrun.getModel vars data frame. That beautiful single line of code will do all this for us, so it'll automatically put the results into a pandas data frame for us. And then at the end, let's throw in a scatter plot using matplotlib. So remember we imported matplotlib.plyplot as PLT. So we just say plt.scatter, so we're going to do a scatter graph of movement versus total infected. So do a scatter graph, and here's the things we want to plot. We want to plot the level of movement from the run data and total infected from the run data. Remember, the run data is a pandas data frame. So we're just going to grab those two columns, level of movement, total infected, and plot them against each other. So before you go running this, I just want to throw up a word of caution. You have to be really careful when you set up lots of different combinations for agent-based models, because you will find that very quickly you'll get into huge numbers of combinations that will bring down even the fastest computers. And I talk from experience, having brought down Mike's computer once using MESA. So let's think about how many different combinations we've got here. So we've got, for each, the two things that we're changing are the number of agents between 2 and 100. For each of those numbers of agents, we'll also need to test each level of movement, which we've got between 0 and 1 inclusive. So we've actually got 11 different combinations of level of movement. For each of those possible numbers of agents between 2 and 100, and for each of those combinations, we've told the model to run 5 iterations. So we've got a lot of different, well over 5,000 different iterations of the model that we're going to have to run. And you'll find when you do this, that initially it will start running quite quickly. And that's because it's going on initially on the running the model with relatively slow, low numbers of agents, like 2 or 3 agents, and relatively low levels of movement, so it becomes quite a simple model. But of course, as it goes on, it's starting to explore more complex models where it's got 98 agents, 99 agents, and they're all moving all the time. So you'll find it will gradually slow down. So be wary. You may want to, before you run this, you may want to change your number of iterations to 2 or even to 1 before you run that, just to make it a little bit quicker. So you'll have sort of just over 1 or just over 2,000 different combinations. Obviously, how quickly this will run will depend on your computer speed. But be really careful, because you can see if I added in another variable to change at the same time, already we've then got another set of combinations that are going to exponentially increase the amount of combinations, and therefore the number of time it's going to take to go through all these things. And you can bring down supercomputers very quickly if you're not careful on this. So just before we sort of sign off, do have a play with that. Have a look at the batch run, and you'll see that you should get a scatter plot at the end, and you should see how the level of infection changes the level of movement, and we would expect there, of course, to be more infection if there was more movement. But just before we sign off, one last sort of exercise for you to do. Agent-based simulation can be used for a lot more than disease modelling. Disease modelling is a handy way for us to show you how to develop an agent-based simulation. But it's useful wherever you've got individual level behaviours that can lead to these more complex population level dynamics. So what I'd like you to do is to think about some potential ideas of applications for agent-based simulation in policing, and to share those ideas on Slack. So come up with some ideas, post them in the group, and see what ideas you can come up with. And maybe even there's an idea for your particular project. My very final thing to say is there's some further reading that I've put up on the slide here. So if you'd like to have a look a bit more into the MESA documentation tutorials, you can find it at that link there. If you'd like to read my thesis, or parts of it, and you don't want to pay £69 to have it in lovely book form, then this link here will allow you to read that, so if you're interested in that at all. I'd also advise there's a really good book called Individual-Based Modelling and Ecology. Ignore the title, it's a really good book for general sort of agent-based simulation interest. And if you'd like to find out more about cellular automata, which we talked about right at the very start, there's a link here where you can find out more about these types of agent-based simulations. So I hope that's all been good fun, and you've learned some stuff there. If you do have any questions, remember I am available on Slack, or send me an email. And if you want to talk through any ideas, I'd be really happy to hear any ideas you might have for agent-based simulation projects. Otherwise, have fun. Post some ideas on Slack for ways in which you think this could be useful, and we'll see you at the next session. Thanks again. Bye-bye.